Today we want to think about interpreting the derivative. We want to think about interpretations of the derivative. What is the derivative telling us in a given situation? So this is where things become word problems. So everybody should be super happy because things have become word problems. That's a better situation because the word problems should make sense. So if you look at your answer and you're calculating the length of a runway for a 747 and you get 15 feet, something has gone wrong. You know that ain't right because the 747 is longer than 15 feet. Our runway is going to have to be longer than 15 feet. Does that make sense? But if you're just doing some generic calculation and it comes out to 15 feet when it needed to be something more like 5,000, who knows? If there's no context, who knows? Maybe 15 is fine. If it's like, oh, how fast was the car going after 6 seconds? If you get an answer of like 380 miles per hour, you're like, oh, well, no, it was not doing it. And then you read the description again. It's like, oh, hang on a second. What kind of car is this? It's like, oh, it's a Toyota Camry. No. Toyota Camry was not doing 0 to 380 miles per hour in 6 seconds. I have done something wrong. But if it's just a generic problem, it says the answer is 380. You're like, all right. The only way I can check is if it's an odd number in the back of the book and it's an even number. So I guess that's it. But if it's a word problem, it's like, oh, the car was going 380 miles per hour. Hang on. No, it was not. After 6 seconds, it should be doing something around like 60 miles per hour. You know what I mean? You should be happy when word problems show up because at a certain level, they have to make sense unless something is very wrong, in which case it's not your fault, right? I like when I mess up writing a problem, I'm off by a decimal place or something like that, and the runway does calculate, according to instructions, the runway does calculate to like 15 feet. And students are like, oh, not Leach said to do this calculation, fucking 15 feet. I'm like, oh, how could you get 15 feet? And then I look at the work, I'm like, oh, because I fucked up. Got it. Then I have to go and change it. I can't change it, so I just have to give everybody points. Because what that only happens after like 20 people have done the problem, said, all right, we're supposed to do this, so 15 feet. Fucking, all right. And then the 21st student will be like, oh, dude, I think there's something wrong with this. I'm like, oh, what? That's not possible. And then all of a sudden, oh, yeah, that's totally possible. Oops. Anyway, let's talk about interpreting the, oh, good, I'm glad I recorded that shit. Let's talk about interpreting the derivative. Mr. Taylor polynomial stuff, record the babbling. We got to remember where we first got this idea for the derivative. We first got this idea for the derivative by thinking the derivative is going to tell us the slope, the tangent line at a point. The important parts of this recall is that the derivative is a slope. Interpreting the derivative is the same as interpreting the slope. So it's this part right here that we care about right now. Derivative is slope. Interpreting the derivative will be the same as interpreting the slope. Like I said, nothing new, just remixing the old stuff. So let's remind ourselves of how we interpret the slope. Let's remind ourselves of how we calculate the slope. Slope is the change in y divided by the change in x. We have new technology now called the derivative that allows us to calculate this even when it's 0 over 0. But the slope is, by definition, the change in y divided by the change in x. So that tells us how we should build the units for the slope. So the units of the slope we'll just take the units of y per the units of x. That's how we build the units of slope. The units of y, then we write the word per, then we write units of x. If we have a function of x, if y is a function of x, it'll be just whatever the units of the function are. So if y is some function of x, then we'll just write whatever the units of the function are. When we say the word per, interpret that as divided by. Units of y divided by units of x. When we talk about percent, we divide that by 100. 72% is 72 per 100. 72 divided by 100. When you make that calculations, it's 0.72 per 1 because we divided by the 100. So it's 0.72 per 1. Because that would be interpreted as divide by 1. 0.72 divided by 1. And we don't write divided by 1. We don't write denominators with 1. So 72% is 72 per 100. Any questions? We have some pretty wild ideas about using percent. We use it for so many things when it doesn't make any sense to use percent. What percentage of the students passed? They're like, 80% of the students passed. But there were only 10 students in the class. Just say 8. Just be like, 8 out of 10. It doesn't make sense to scale that up to 100 when there are only 10 people to begin with. You know what I mean? It's really weird, our relationship with percent. It's especially funny that we keep trying to standardize things. We don't really understand what the standardization means. And we combine that with our exceptionally poor track record of estimating probabilities of things. We're just really bad at that. We like to think that we're super rational and we think about rational things, but we're super irrational, but we're really good at rationalizing. You know what I mean? So anyway, that's all beside the point. This is how we build the units of the slope. We take the units of the function, we write the word per, Then we write the units of x and then see if that tells us something. So for example, is there one L in travel? Is there one L or two L's? Hey Siri, how do you spell traveled?
Troubled.
One L. Dang it.
Oh.
That's one of those words that no matter how I spell it, it looks wrong. I don't know why. And kind of there are three L's, but one gets crossed to make a T and the other one gets a little circle to make a D, but that's beside the point. Let F of T be the distance traveled, let's say in miles at T hours since the start of a trip. So let's suppose that F of T is a distance traveled in miles at T hours since the start of a trip. The first thing that we'll want to do is just construct the units of what the derivative will be. We're just going to take the units of our function and say per, and then the units of our variable. So the units of f prime will be the units of f, and then we'll write per, and then we'll write the units of t. The units of f are miles, then we write per, and the units of t are hours. So that tells us what the units of the derivative are going to be. Miles per hour. Let's suppose that we have a function that measures our profits when producing a certain number of units. Our profit's going to be measured in thousands of dollars or kilodollars. I don't think we ever say that, but thousands of dollars. And X are just going to be measured in units. The units of our derivative will be the units of the function, then we write per, and then we write the units of our independent variable x. The units of our function are thousands of dollars. Per, then the units of x are just, well, units. The first step for interpreting what the derivative is telling you is to write down the units of that derivative. Step one, write the units of the slope. Oh, hang on, the derivative. Now, back when delta y divided by delta x had to have some positive values, we didn't have 0 over 0, we had some positive values, that would be an average rate of change. But when we're talking about derivative, we're talking about instantaneous rate of change, and that's step 2. Make it instantaneous at a point. That's the at a point part. So once we write down the units, then we just interpret those units as an instantaneous rate of change. So in our first example, f of t is the distance traveled in miles at t hours since the start of the trip. If we had, say, f prime of 3, this would be our instantaneous rate of change of distance in miles per hour after 3 hours. How fast we were going after 3 hours. So for example, oops. If I see something like f prime of 3 using the same f, because I didn't leave space to write this in, you see what happened. We would interpret this as after 3 hours, our instantaneous rate of change, or in this case, our speed, was 65 miles per hour. I'll call it speed, and because speed is instantaneous rate of change of distance with respect to time. Any questions? Step 1, write the units of the slope. Step 2, just interpret it instantaneously. Remember, the derivative is telling you what's going on at a point. It's a speedometer reading. At 3 hours into our trip, our speedometer reading says 65 miles per hour because we're good law-abiding drivers. Then we get pulled over. It's like, well, it's a 40 mile per hour zone. Dang it. My car has like the GPS and it knows the speed, for the most part, knows the speed of the road that I'm driving on. And it like displays that in my speedometer. And it just makes me feel like my car is going to narc on me at some point. So it's got like a little sign. It's like, speed limit is 65. And it's like right next to my speedometer. So on my speedometer, it's like, oh, I'm going 72. And then right next to it's like, oh, speed limit is 65. I'm like, oh, quit nagging me, car. And I'm worried that if I slow down because I see a like highway patrol or something like that, I probably wouldn't slow down at 72. But if I'm going like 85 or something like that, like, oh, maybe I should slow down. I'm worried that the car would be like, oh, you know, he was going like 85, like a mile back. And then the police car will have a little flashing thing on their dashboard that says, hey, you should go get that guy. He'd be like, oh, why? So, because a couple miles back, his car told me that he was going 85. So let's go get him. And the highway patrol be like, all right. And that's how robots are going to take over the world. What are we talking about? Oh, yeah. So step one, we just write down what the units are, units of function per units of variable. Then we just interpret that instantaneously. What's going on at that moment? Because that's what the derivative tells us. For this second one, we have profits to be increasing or decreasing depending on whether we produce, how many items we are producing. So for example, using the second one, if we see a statement like P prime of 3,000, P prime of 3,000 is negative 0.5. This would say at a production of 3,000 units, because that's what the input represents. At 3,000 units, our profit will be decreasing by 0.5. That's really excessive. It doesn't matter. By $0.5,000 per unit. What that tells us is that if we make one more unit, our profits will be decreasing by $500. That seems excessive. I don't know what these things are. So. Here to read the numbers, not interpret them. I know that kind of flies against the problem. The answer should make sense, but it's a bunch of numbers that I made up on the spot. The way we can interpret this is that if the input increases by 1, this is how much our output would increase by. So after 4 hours, if this continues, we will drive 65 more miles. If our production changes from 3,000 to 3,001, I was going to do this in kilounits too, that's why. If our production goes from 3,000 to 3,001, our profit will decrease by $500. Any questions? That's how we will interpret the derivative. We write down the units of the slope, and then we just make it instantaneous. It's what's happening at a point. It's a speedometer reading. One thing to note about these changes in this previous one, I said if this continues after 1 hour, our distance will increase by 65. That's just how far extra we go if this continues. We still don't know how far we've gone. This is just how much things have changed. So we're just tracking how much things have changed. Any questions? Comments? Snide remark? Everybody looks so sad. So sad. Y'all give me this. All right. That's the big thing. Today we want to interpret the derivative. The derivative is a slope, so we interpret it as such. To start that, we write down the units of the slope. Then we just think about it in terms of an instantaneous rate of change. Let's make it instantaneous. At this moment, this is what's happening. All right, that's gonna do it for today. That's, no, today's Thursday. That's gonna do it for today. I'll see you all on tomorrow. Everybody have a good day, and thanks for playing.